We can draw a picture or a graph of a sequence. In the usual way, a sequence is really just a function of the integers n. So f of n is an, which, as we saw, often has a formula. It might be 2 to the n over n factorial. And we can draw a graph of this function. Instead of being a continuous graph, it's a graph of discrete dots. So the first point on the graph is 1 f of 1, or 1a1, and the second point is 2a2, 3a3, etc., etc. Nan is the nth point on the graph. So the n's are along the horizontal axis, and the ans are the coordinates on the vertical axis for each of these points. We see here the graphs of two sequences. We have the alternating sequence minus 1 to the n over n, and the sequence 2n cubed minus 1 over n cubed. And notice these dots have patterns, and your mind might wander back to Calculus 1, where you saw pictures of functions with horizontal asymptotes, which meant that as x went to infinity, the function had a limit. And we'll talk about that in a moment. For now, notice a couple of things, that as n approaches infinity or gets larger and larger, 2n cubed minus 1 over n cubed gets closer and closer to 1. So the y values on the graph get closer and closer to 1. And for the sequence on the left, the alternating sequence minus 1 to the n over n, as n gets larger and larger, the values alternate between positive and negative values, but they both get closer and closer to 0. Both of these graphs display limiting behavior. And we can make that precise. The definition is the same as we had for functions of x in Calculus 1. A sequence an, which is really just a function of n, has a limit L if we can make the terms an as close as we like to L by taking n sufficiently large. So in other words, the limit as n approaches infinity of our function of n is L if an approaches L as n approaches infinity. If the limit exists, we say that the sequence converges. And if the limit as n approaches infinity doesn't exist, we say the sequence diverges. Graphically, if this limit exists, then the graph of the sequence has a unique horizontal asymptote, and that asymptote is y equals L. So we saw for our previous two sequences, both of the graphs have horizontal asymptotes. The one on the right has a horizontal asymptote y equals 1, and the one on the left has a horizontal asymptote y equals 0. So the limit of the sequence on the left does exist, and it's 0, and the limit of the one on the right exists, and it's 1. So both of these sequences converge. Now we can write an equivalent definition of convergence here. A sequence an has limit L, and we write the limit as n goes to infinity of an equals L, or an tends to L as n tends to infinity, if for any number we can pick epsilon, no matter how small epsilon is, there's some integer out there, whether it's 100 or 1000 or 1 million, with the property that for every integer bigger than that one, the distance between an and L is less than epsilon. And I can make that epsilon as small as I like. So I can get the values of the sequence as close as I want to L from some point on. We don't have to reinvent the wheel here. Sequences are really just functions of the integers n, and if when we substitute x for n, where x is a continuous variable and can take on real values, if that function makes sense and it has a limit, then the ans must approach the same limit as n goes to infinity, because the values of n are a subset of the values of x. So the graph of the function that we construct in this way, y equals f of x, is really just what we get by joining the dots on the graph of the sequence. Here's an example to show what I mean. Let's suppose we want to figure out if this sequence on the left converges or diverges. Sequence is 2 to the n minus 1 over 2 to the n, and n runs from 1 to infinity. Well, in its description as a function of n, I can replace the n by x, and I get a nice continuous function. And that function, as x approaches infinity, has a limit. Now, the graph of y equals f of x here, which is 2 to the x minus 1 over 2 to the x, contains the graph of the sequence. The graph of the sequence is just a bunch of dots on the graph of this nice continuous function of x. So those dots must follow the same path as the graph of y equals 2 to the x minus 1 over 2 to the x, and if that function has a limit, they must have the same limit. If I can replace the n by an x in this way and calculate the limit, then I can get the limit of the sequence. So the limit as x tends to infinity of 2 to the x minus 1 over 2 to the x should be the limit of my sequence. And I know how to cope with this from Calc 1. I divide numerator and denominator by 2 to the x, and I get the limit as x approaches infinity of 1 minus 2 to the minus x over 1, which is 1. So my sequence converges to 1. Now I can do the same thing for the sequence on the right. I can replace the n by x, and I get a function of x, and I can take the limit as x approaches infinity of that function of x. If it's finite, then that's the limit of the sequence, and if it's plus or minus infinity, that's also the limit of the sequence. We'll say the sequence diverges to plus or minus infinity. Well, let's replace the n by x in b, and I get the limit as x goes to infinity of 2 times x cubed minus 1 over x cubed, and that rational function I can divide by the highest power in the denominator to calculate the limit, and that limit is equal to 2. So our sequence on the right converges to 2.